to review Numeric series. Again, we would have done this part of our curriculum in something called endpoint analysis, but so we hadn't quite gotten to it yet, although most of it is pre-cal, so hopefully you remember some of it from pre-cal. So this is a multiple choice question from AP on numeric series. So here's how you can tell the difference, and you know you're dealing with a a numeric series rather than a power series. There ain't no x's. There's only n's. N for numeric. So which of the following series converge, and further, which of them converge to the number 2? This is a clue right away. As soon as somebody gives me an infinite sum or asks me for an infinite sum of a series, I only have one kind of series I can do that for, and that's a geometric series. So when I look at the first one, this does not look geometric to me, right? It does not look geometric. Plus, since it's not geometric, I'm already suspecting that it's going to be eliminated. And the other thing you want to think of is every time when you're asked about a series converging, do the terms go to 0? Because the nth term test for divergence, if your terms don't go to 0, you automatically don't converge. Now, if your terms do go to 0, you might converge, but you might not. But if you look at these terms, I just start writing out a couple. If I start writing out a couples, I'm going to make n equal to 1, right? I'm going to get 2 times 1 over 1 plus 3. And then my next term is 2 times 2 over 2 plus 3. And then 3, 2 times 3 is 6, and 3 plus 3 is 6. These terms, not the sum, the terms themselves, the terms are not approaching 0. Therefore, diverge by the nth term test for divergence. And that again goes along with my intuition that if they're asking me if a series converges to a number, the only way that I have of generating an infinite sum is a geometric series. So I already suspected this one was going to be excluded. So notice that down here I can exclude 1 and I can exclude D already. So now I'm thinking, okay, so these two kind of sort of look geometric. And if you remember, for geometric, you're looking for a common ratio to the n, right? So the only issue with this one is the -8, right? But that's okay. This is -8 times -1/3 to the n, right? Does that make sense? Can you see that? Right? This is really, right, 1 to the n, 3 to the n, negated. And this one is 1 over 2 to the n, isn't it? So this seems to be the simplest one to look at, so let me just investigate the sum. This is definitely geometric. Here is my common ratio, and my common ratio needs to be what? Less than 1 in order for convergence. It is, so I have convergence. And now my infinite sum formula is the first term, or A, over 1 minus that common ratio. So what do I have here? 1 minus a half, and what is my first term? Plug in 0, 1 over 2 to the 0, 2 to the 0 is 1, 1 over 1 is 1. And then I think you can see that this is indeed 2, right? Because this is 1 minus a half is a half, 1 divided by a half is 2. So certainly 3 is good to go. So my answer is either C or E, right? Because B is out because 3 definitely needs to be included in your answer. So my only issue is this one. So I look at this and I say, well, my common ratio is the absolute value of -1/3, but the absolute value of negative 1/3 is 1/3, and that is less than 1, right? So now I say, well, what is my infinite sum? 1 minus negative 1/3. And here's the trap with this problem. Not enough kids pay attention to what the first term really means. This is kind of mean, right? Look at what I start with. A 1. So what is my first term? My first term is negative 8 times negative 1/3 to the first power. And isn't that 8/3? Right? Because negative 1/3 to the first is negative 1/3 times negative 8. So the first term is 8/3 here. So this is 8/3 over, what is this? 1 plus 1/3 is 4/3. And when you divide that, the 3's cancel out and you get 8 over 4, which is indeed 2. So this was kind of a mean problem, right? You could very well know the nth term test, and you could very well know that you need a geometric series in order to calculate an infinite sum. And you probably would have gotten this right, and you probably would have gotten that right. And indeed, for the statistics for this, most people that got this wrong chose C. But the answer is actually E, right? So E was the correct answer. The first series, I used the nth term test for divergence to see that the terms themselves, it didn't look geometric. So I just plugged in that n starting with 1 here and showed that yes, this does diverge. This one I used the geometric series test for convergence, recognizing that r was negative 1/3, but my first term, since again I was starting at 1, and that was a little mean, right? That's why I have my little horn guy here, right? This was a little mean because this one started at 0. So my a was equal to 1, but here my a was equal to 8/3 because a is your first term. All right, so I'm going to talk some more about geometric series as this PowerPoint is going to talk about when does a numeric series converge. So any numeric series, you should always start with the easiest test, not for convergence, but for divergence. Look at the limit of those terms, especially if it doesn't appear to be geometric or anything like that. Do the limit of your terms go to 0? That is, if your terms do not go to 0, your series definitely diverges. That is the one and only divergence test. You have one divergence test, and this is it. But it's an easy one to run, so you might as well kind of get in the habit of checking it. If you've looked at your terms, and your terms do go to 0, then you've got to go on. If my terms go to 0, is the series geometric? And in order for it to be geometric, I need to find a common ratio and see if my common ratio is less than 1. If my common ratio is less than 1, my series will converge. Oops, sorry. Not only will my series converge, but this is the only series that I can give you a formula for finding the actual sum. First term over 1 minus your common ratio. If it's not geometric, is it a p-series and all my terms are positive? P positive. And a p-series looks like this. If your series with positive terms is 1 over x to the p, as long as p is greater than 1, the series will converge. And then, of course, conversely, and the same up here, if the common ratio is greater than or equal to 1, then you diverge. But again, we're really considering we want convergence, so I don't really care about this. And the only reason I care about this nth term test for divergence is just so I don't have to run the rest. If p is greater than 1, if it's a p series, p is greater than 1, the series would converge. If p is less than or equal to 1, the series diverges. All right, so let's practice a couple of those, geometric and p-series. Use the geometric series test for convergence, that's in red, common ratio less than 1. P-series test for convergence is where I want p to be greater than 1. So, do these numeric series converge? So hopefully here this looks geometric to you, right? I have a ratio raised to the nth power that looks geometric, and I have this common ratio. And that common ratio is less than 1, so yes. If it converges and it is geometric, they probably will ask you for the sum. Go find my first term. N is equal to 0, so my first term is 1. So this is 1 over 1 plus 2/3, which of course is 1 over 5/3, which is 3/5. Notice when I'm not dealing with geometric, I will never get to evaluating and telling you what the infinite sum is. Now this doesn't really look geometric, does it? Firstly, I'm going to do this using my exponent rules. Isn't that true? Now it looks a little more geometric. Further, I'm going to use my algebra 1 rule, another algebra 1 rule, and say e to a negative exponent is the same as 1 over e cubed. So again, this, I hope you can see, is a common ratio raised to the n power that looks geometric. And now I just have to look for my common ratio is 1 over 2.7-ish cubed less than 1. Tis. So what's your infinite sum? Oops, sorry. 1 minus. And up here is a, my first term, since I start at 0. E to the 0, which is 1. Please don't cross out those e cubes. All right, here's another one. This one's a little trickier. Firstly, it tells me that x and y are both greater than 0. Oops, this needs to be a 1. Do you see why? Why? Get it? And I can't be putting 0 in there into the denominators. Okay, so what is this telling me? So firstly, I have to look to see this does look geometric. I have a ratio raised to the n power. And what do I need? Just like these other ones, I need my common ratio. To be less than 1. So what does that mean? Since I have algebraic terms here, right, I need to say what that really means. And now do you see what I can eliminate because of this statement? If x and y are both greater than 0, the ratio of those is never going to be negative. So I really only need to deal with x over y squared being less than 1. Can you get x by itself there? So x has to just be less than y squared. Then my common ratio will be less than 1, and then my geometric series will converge. Can you tell me what the infinite sum will be? One minus my common ratio. But what is my a? My a is right? X over y times x over y squared to the first. So isn't that x squared over y cubed? That goes here. And now I can clean this up because my denominator is actually, change color so it's obvious where I'm going here. Right, I'm going to take this denominator and I'm going to clean it up. So that's y squared minus x all over y squared, and this is x squared over y cubed. So that would be x squared over y cubed times y squared over y cubed minus x. That would cancel out, leave me with a y. Lost my place. Where am I? Oh. Y cubed minus x. Okay. So that one was a little messier because it just because it had too many variables. But the key part for each one of these is to recognize that your common ratio and your infinite sum series, right? So each time for geometric, I'm looking for a common ratio, investigating whether that common ratio is less than 1. And then if I am asked for an infinite sum, the common ratio is in the denominator, 1 minus r, 1 minus r, 1 minus r. And then the infinite sum, you just have to be careful, like that warm-up, right? The numerator isn't always a 1. The numerator is your first term, and your first term is determined by your expression and which index you start with. So be careful. All right, let's try some p-series. So 2 questions here. Which of these p-series converges? Now this question I find kind of nasty because they're asking which of the p-series converges. This is first. So I don't care whether this converges or not. It's not a p-series. So one of the objectives of this question is, do you recognize a p-series? So n cubed, I hope you know, I mean, that's a function, right? That's a cubic function, right? The n behavior shoots off to infinity. So this certainly doesn't converge. But even if it did, it wouldn't matter for this question because they asked me, first, is it a p-series? Then does it converge? So this second one converges, doesn't it? Do you recognize it from what we just did? Right? My common ratio is 1/3, which is less than 1. So yes, this converges, but I would get tricked in this question. It's not a p-series. So it converges, but it's not a p-series. So they're trying to get you to recognize the difference, right, between what's a geometric series and what's a p-series. Is this a p-series? This is 1 over n to the 1/2. So that is a p-series, so I can run my p-series test on it. I ran the geometric series test on this, and I got convergence by the geometric series test, but that's not what they asked. So this is indeed a p-series, so yes, it's a p-series. Now ask, does it converge? P is is less than 1. So what does that? Look at your rules for p-series. That means diverge for p-series, right? This exponent has to be greater than 1 in order to converge. That's your p-series test. So is this a p-series? Right? 1 cubed is just 1, isn't it? And n to the 1/2 times 3 is n to the 3/2. So can you run the p-series test on this? Yeah. And what it is the p-series form, and p is greater than 1, therefore by the p-series test, this p-series converges. This geometric series converges. Right? So I got converge here. This series, by the nth term test, diverged, but it wasn't a p-series anyway. This converged, but it was geometric. This was a p-series that failed the p-series test for convergence because the p-value was less than 1. And this was a p-series, yes, and passed the p-series test for convergence because your exponent p there was greater than 1. So notice the difference between the language of this question and the language of this question. This one just says which of these series, it should say. Okay, so I just need to know if I have convergence. It doesn't matter which test I run. So far, I'm running the Geo test and the p-series test. So, makes me a little nervous. I think I know what to do with this, right? Let me go to this one. Isn't that e to the negative 1 to the n? And what did we do with this before? So what test are you running on this? This is the Geo Series test, and the common ratio r, which is 1 divided by 2.7-ish, is less than 1, so yes, converge. What about this one? This is not geometric, is it? It's the only other test you got so far. This is a p-series, right? But p is equal to 1, therefore fails the p-series test for convergence, because remember, for p-series, your p, that exponent has to be strictly greater than 1. This is actually, some of you may recognize this. This is a very famous series, right? It's 1 over 1 plus 1 over 2 plus 1 over 3. This series does not converge, even though the terms do go to 0, right? These terms are going to 0. This is the best example of showing just because your terms do go to 0, your series does not automatically converge. If your terms don't go to 0, you definitely diverge. Anybody remember the name of this series? This is the Harmonic Series, and it does have a tie to music. That's why it is called the Harmonic Series. This is the Harmonic Series, and the Harmonic Series does not converge. So the only thing I have left is this guy over here, which kind of made me worried because I was unsure about what was going on with this. And really, this isn't a numeric series because I have an x, so I probably shouldn't have put this on here. But I only wanted to show you this because no matter what x you put in, what is the highest, since this is the absolute value, what does this really look like? What's the highest value of sine x? Absolute value. Isn't that 1? So this really is the same thing as looking at 1 over n squared, so it really is a p-series, right? And it's kind of you're kind of sort of comparing, right, to the p-series where p is greater than 1, so you pass the P-series test for convergence. All right, so that's geometric and P-series. If you remember series from pre-cal, these are the two that probably stick in your head a little bit, geometric series and the P-series. All right, next. These are your comparison tests that you learned in pre-cal, but we also did them again for improper integrals. Now, this is not on this year's AP, so I'm going to gloss over this. But if you can find a bigger similar series with positive terms, so for instance, we did this with improper integrals, but if you have, instead of 1 over n squared, you have 1 over n squared plus 1, right? You can compare that to 1 over n squared, and since, right, is, you know, a bigger series because 1 over n squared, right, lies on top of, let me write that better, 1 over n squared is bigger than 1 over n squared plus 1. I know this converges, P series, P greater than 1, so convergent. Therefore, by the DCT, this very similar but smaller series converges as well. And again, for numeric series, we're just interested in convergence, so I don't really care about diverge. I don't want to show that anything diverges. This is the direct comparison test for convergence. And then the issue with the direct comparison test that I caught some of you on the quiz was if you're showing convergence, the function you know has to be above it. If you're showing divergence, the function you know has to lie below the one you don't know. So, right, so position or size matters for the DCT. If that's challenging or you don't have the right orientation, for instance, I want to show divergence but my function lies under, then you can go to the limit comparison test. I just need to know that they're similar. Notice I don't care about size and which one, right? If one function is above or below the other one, they just have to be similar. And if I do a limit of the ratio, set up a ratio between the function I know and the function I don't. So for instance, 1 over n squared compared to 1 over n squared plus 1. If I do the limit of this as n goes to infinity and I get a limit that is between 0 and infinity, then both of the series converge. Again, you don't have to worry about this. So I'm not going to practice these ones. We practiced it really when we did improper integrals, and also they have said that comparison tests are not on this year's AP. All right, next test. Notice that nothing I've been dealing with before all the tests that we've been running have been on series that have all the same sign. What if your signs alternate? You want to look for this issue, and I don't care. Sometimes it's -1 to the n if n starts at 0. Sometimes it's -1 to the n minus 1. You know, whatever. I don't really care about this. This is a sign alternator. Do you have some kind of sign alternator? And then this is some other expression for your terms. If this expression for your terms gives you all positive terms, and the only reason your signs alternate is because you have a sign alternator, and that's what this next statement says. If you have a sign alternator, but each of these terms on their own would be positive. Further, every successive term is smaller than the one that came before it. And the limit of your terms are going to 0. Then your series will converge by the alternating series test for convergence. So this is sometimes a little clunky and kids are like, wait, what? Basically focus here. You know how you had the nth term test for divergence? And we said if your terms do go to 0, you cannot automatically say you have convergence. And the best example of that is the harmonic series. If your signs alternate, it is enough. This sign alternator makes it so if your terms are positive and they're getting smaller and they go to 0, you will converge by the alternating series test for convergence. So let's practice that. So notice this is a P series, this is the harmonic series, and what do we say? The terms do go to 0, but it is a P series, so this diverges because even though the terms go to 0, P is equal to 1. So it fails the P series test for convergence. But look at this. This really is 1 over n, isn't it? There's 1 over n. The only difference between the expression on the left and the expression on the right is the sign alternator. Do you see that? 1 over n, 1 over n. The harmonic series 1 over n diverges because P is equal to 1. This is the alternating harmonic series. The only difference between the one on the left and the one on the right is the sign alternator. So I have the sign alternator, check, right? -1 to the plug in 1. 1 plus 1 is 2. -1 squared is positive. Then plug in a 2. 2 plus 1 is 3. -1 to the third is -1. Right? There's my sign alternator. Then this is my a sub n. My a sub n is 1 over n. Those terms are all positive. And the terms go to 0. With the combination, so check terms go to 0, check terms are positive. The most important check is that I have the sign alternator. This series converges by the alternating series test for convergence. So how about this pair? Can you see what's going on here? Can you see that I've got the same kind of thing? This is also a P series, 1 over root n. And can you see that I really have 1 over root n here? This series diverges. Why? P is less than 1, right? Because P is a half. So this failed the P series test for convergence. This over here has a sign alternator, 1 over n to the 1/2. Terms are positive and go to 0. So check 1, check 2, and all important, check 3, converge by the alternating series test for convergence. So this one throws kids sometimes, and honestly it throws the kids who overthink it. Really, this takes a comparison test, or you can kind of think osmosis, right? I really have a constant here. There's a constant of 1/2. Take the constant out front. This is really 1/2 times 1 to the n, but isn't that just 1 over n? So this is really the harmonic series, right, which diverges because you fail P-series test. 1/2 times a divergence series still diverges. So can you see what I'm going to do over here? I also have a 1/2 that I'm going to suck out front, but this time I have 1/2 times, whoops, that's terrible, isn't it? -1 to the n over n, right? And even though I have an n instead of an n plus 1, it just means my first term is going to be negative, right? Because I'm going to plug a 1 in for n. But this is still right, 1 1 over n, which diverges on its own, but you have your sign alternator. Your a sub n is 1 to the n. Terms are positive, right? When you start putting in 1, 2, 3, 4, those are all positive, and the terms go to 0. Therefore, 1, 2, and all important 3. This series converges by the alternating series test, and 1/2 times a convergence series is a convergence series. Again, or you could think, oh, I'm going to do a comparison of 1 over 2n to 1 over n and run a comparison test on it if you like. All right, so we've done geometric series, P-series, and alternating series. Now, what if I don't have any of those? This is not the only case this new test is used, but it is very common if your series has any factorials or exponential terms or lots of powers. Then you're going to use another test. This test is called the ratio test for convergence. So maybe you remember this from pre-cal, maybe you don't. This is confusing, but I'll tell you what this means. The ratio test is a limit, so you do have to do a limit, and you have to do a limit of a ratio, and you want the limit of that ratio, and this should sound familiar, kind of sort of sounds like geometric, right? It's just that when we were doing the geometric series, we didn't have this limit issue. If it was geometric, we only had common ratio needed to be less than 1. Now we're going to take a limit of the absolute value. So I don't care if I have an alternating series or not, because I'm only going to be talking about the absolute value of the ratio. And conceptually, if you care, what this is forcing a common ratio when one doesn't happen. So it kind of sort of is forcing something into a geometric series that isn't actually geometric. Don't worry about that if that doesn't make any sense. Focus right now on, do I have any factorials? So those are Yale points, right? Do I have exponential terms like 2 to the n, 5 to the n, e to the n, or do I have a whole bunch of powers like x plus 1 cubed over n squared or something like that? If I have a lot of these issues, that's when usually the ratio test is the best test to use. So let's do some of those. Right, so oh my gosh, look at all those. So I'm going to do them one at a time. But I want you to look at them first. I left them all up here for you to look at globally. Do you see how each one of these involves a factorial, an exponential, powers, or lots? And the only one that is slightly different is this ln one here, is the only one that's not an exponential, a Yell point, or a power. Okay, but everybody else has got yelling all over the place, exponentials all over the place. So this is where I think to use, right? It's not p-series, not geometric, not alternating, or even if it does alternate, it's got too much crap going on. So this is where I think to use the ratio test. So let me start with the first one. So the ratio test is a limit of the absolute value of a ratio. And the ratio is a ratio of one term to the previous term. What that normally looks like, and it's as n goes to infinity. How you'll usually see this written is your terms are a sub n's, right? So if I have a term n plus 1, compare it to the term that came right before it, which is a sub n. Now I could have put a sub n here and a sub n minus 1 here, but this is usually the most common way. This limit has to be less than 1 in order for the series to converge. The only thing that is different from the ratio test is for divergence. The series diverges if this ratio is greater than 1 of a term compared to a previous term. Notice there's no equal sign on either one of these. The ratio test is inconclusive. It just means the ratio test isn't a good test to run. It means you need to run another test, a different test. Maybe you should have recognized something geometric, or maybe you should have recognized a p-series, or maybe you should have done a comparison test. If this ratio is equal to 1, the ratio test is inconclusive. Go do another test. That's annoying. Okay, so you want to get your best scenarios to get this ratio to be less than 1. If you get your ratio to be greater than 1, well, then you know you don't have convergence, but at least you know you have divergence. But if this ratio equals 1, you have to go and do the whole thing over again with a different test. P-series, geometric series, alternating, something. All right, so let's start. So for this first one, I'm going to do a limit as n goes to infinity. I don't really need absolute values for this because everything is positive. So in for n, put n plus 1. And then compare it to the original. Now this fraction within a fraction thing is kind of messy. So I actually never write the statement that way. I always start like this. And I'm going to drop the absolute value bars because I don't have anything negative. I always do this. I put in my n plus 1s, and then I do what I would have done here anyway, which is multiply by the reciprocal. I just skip this step. And I need this to be less than 1. So now I'm going to take this piece and do algebra. On all of this. I'm going to do algebra, then I'll take the limit, and then I'll see if it's less than 1. So let me go off into my workspace. I'm going to take this off into my workspace. I'm going to say, hello, 3 to the n plus 1. You could be written as 3 to the n times 3, couldn't you? And then n plus 1 Yale point could be written as n plus 1 times n factorial, right? That's just me being super clever. Why did I want to be super clever? Well, look at what this fraction is. And look who I can get rid of. By. And what am I left with? I've cleaned this up, this whole green mess up, and I only have 3 over n plus 1. Now take the limit as n goes to infinity and tell me what that limit is equal to. Well, I took pre-cal and I paid attention, right? This is the end behavior of a rational function, where the power of your numerator is less than the power of your denominator. So this limit is 0, and 0 is less than 1. So by the ratio test for convergence, this numeric series converges. Woot woot! Let's do another one. So I'm going to do the second one. So I'm going to set up a limit. And again, I thought to do the ratio test because I see powers and exponentials. I'm going to put n plus 1 into here and n plus 1 into here. And I'm going to multiply that by the reciprocal of my original. And I need this ratio to be less than 1. So now I'm going to take everything in here and simplify it using my algebra skills. So I'm going to take this here, and I'm going to say, well, there's not much to be done with n plus 1 squared minus 1. I mean, I could square that out and combine like terms, but I just don't really think I need to. And that comes with experience, right? I really don't care what the middle terms of these things look like. I care about, I'm going to infinity, I care about the fact that this is n squared. I split this up because I have a 2 to the n here. Now this by, and now go back and think about what the limit will be. I have the limit of n plus 1 squared minus 1 over 2 times n squared minus 1. And I'm taking the limit as n goes off to infinity. Now again, look at what I've got here. I've got the highest power in my numerator is n squared. The highest power in my denominator is n squared. So my powers are even. What does that mean? That my limit is as you go to infinity. Right? Remember your pre-cal? It's the ratio of the leading coefficients. This is going to be n squared. What's its coefficient? This is n squared. What's its coefficient? So this limit is less than 1, which makes me happy, which means I have convergence by the ratio test. Alright, let's do another one. So again, not quite sure about this ln thing, but this is definitely exponential. I don't see anything negative, so I don't really need my absolute value bars. It's just habit at this point. But I'm going to put n plus 1 in here and n plus 1 in here. And why don't I just go ahead and do this? 5 to the n plus 1. Is that less than 1? I don't even have to go into my workspace this time because that was simple enough. That cancels out. And I have ln of n plus 1 over ln of n. But I've got a 5 down here. So remember, you're talking about as you go off to infinity. So can you think about what's going to happen as you go off to infinity of the ratio of ln of a million plus 1 divided by ln of a million? Ln of 1 million trillion plus 1 divided by ln of 1 trillion, right? This ratio is going to go to 1. So what is my limit going to be? Which is less than 1. Therefore, I have convergence by the ratio test. Ratio test for convergence. If the limit of the ratio of successive terms is less than 1, then by the ratio test you will have convergence. All these things are proven. We're just using them. Somebody else has already proven that these tests work. All right, let's do our last one up in this row. Oh my Lanta, look at everything that's going on there. You're like, ah! Stop yelling at me! All right, I have to put an n plus 1 here, an n plus 1 here, and an n plus 1 here. Yield point, n plus 1 yield point, 3 to the n plus 1, which we're pretty sure is useful to write that way, right? And then times the reciprocal. Hey, those 3 yield points are going to go away, right? I think I can get that n factorial to go away, and I already see that that 3 to the n is going to go away. And I need this ratio to be less than 1 to get convergence. So let's see, what can I do here just right away? I think I might have to take this one off into my workspace, right? Right, I need to take all of this nonsense. I need to organize this. I'm not confident enough to just work within there, but as you get experience, you will, right? You won't have to go off into your workspace every time. So I'm going to take the inside part here over here. Now that's n plus 4 factorial, right? This is n plus 4 factorial. But look at what I have down here, n plus 3 factorial. So this comes from some factorial knowledge, right? N plus 4 factorial is the same as n plus 4 times what? And if that's hard for you to buy, just start playing with factorials, right? What if n was 7, right? 7 plus 4 factorial is 11 factorial, which is 11 times 10 times 9 times 8 times 7 times 8 times 5 times 4, da, da, da. But isn't that the same as 11 times 10 factorial? That's all I've done right here. Now, why did I want to do that? Because what's in the denominator over here was n plus 3 factorial. So I'll be able to cancel those out. Now I've still got this 3 factorial, which is going to go. I have 3 to the n, which is going to go. And I have a 3 to the first, which is going to stay, right? Nobody's going to cancel out with that. And then the only thing I have left here is an n plus 1 factorial and an n factorial in the numerator. So guess what I want to do? I want to do this same kind of thinking, right? This is n plus 1 times n factorial. So now look at how many things are going to go away, right? B, by, a b, a by, a b, by, b, by. And what am I left with over here? N plus 4 in the numerator, and that's it, right? Everything else is gone. And what's in my denominator? N plus 1, and what else? A 3, right? So what is this ratio? Once again, you have, going off to infinity, you have power in the numerator is equal to power in the denominator, so your limit is the ratio of coefficients, which is 1/3, which is less than 1, which makes me happy because by the ratio test, I have a convergent series. So every one of these functions series converged by the ratio test. All right. So now let's do these two. I bet you can kind of think what's going to happen here, right? If I did 4 examples of convergence, what do you think is going to happen? So now I'm taking the absolute value, so what do I care about this negative, right? Now remember, I have to put an n here, n plus 1 here, and an n plus 1 here. So I've got -2, which eventually is just going to be turned into a +2, right? And I have n plus 1 minus 1 over the square root of n plus 1 plus 1. It's the square root of, right? So all of that's to the 1/2 times the reciprocal. And I need for convergence that ratio to be less than 1. So firstly, do you see that this is just an n, right? Right, this is just -2 to the n. Right? And then what is this? This is -2 to the n, and this is -2 times -2 to the -1, right? Isn't that -2 to the n minus 1? And this is n plus 2 to the power of 1/2, and this is n plus 1 to the power of 1/2. So who's going to go away here? -2 to the n goes away with -2 to the n, right? Which takes care of that. So I am left with taking the limit So what again do we have here? We have n to the 1/2 and n to the 1/2. I don't care about this plus 1 and plus 2, right? So again, I have this is going to go to 1 as you go off to infinity, right? This is all going to go to 1. I don't want to cancel it out, right? This goes to 1, leaving 1 over -2 to the -1. But what is that? Isn't that right? 1/2. But now I'm going to do the absolute value, and isn't that right? The absolute value of -1 over 1/2 is 1 over +1/2, which is 2, which is greater than 1. Therefore, I fail the ratio test for convergence. But I know I definitely diverge because my ratio is greater than 1. Again, not that interested in series that diverge, so I'm not going to do as many examples of that, but I wanted to show you a place, especially with that whole -2 to the -1 down in the denominator, was a little bit tricky. Let's do the last one. So I need to put n plus 1 in there, n plus 1 in there, and n plus 1 in there. So I have 3 to the 2 times n plus 1 plus 1, 9 to the n plus 1, which I'm pretty sure I should write like this, and then n plus 1 to the 1/2. And then I'm going to multiply that by the reciprocal of my original. Ooh, look at what I'm doing here. See what's going on there? Now, what the hee-haw is this? What do I have here? This is 2n plus 2, but 2n plus 2 plus 1 is 3 to the 2n plus 3, isn't it? But isn't that 3 to the 2n times 3 to the 3rd? And you see why I wanted to do that? I wanted to rewrite all of this because now I can say 3 to the 2n crosses out with 3 to the 2n. 9 to the n crosses out with 9 to the n. And then what do I have here? 3 cubed is 27, right? And 27 is 3 squared times 3, and 9 is 3 squared. So I'm just going to end up with a 3 to the 1st there, and a 3 to the 1st is going to cancel out with that 3 to the 1st. So what is left here? Do I have anything in my numerator? Oh yeah, I have n to the 1/2. And what do I have in my denominator? So you're going off to infinity. What is the ratio when you're going from n to the 1/2, and I don't care, n plus 1, n plus whatever, to the 1/2? This limit is 1. Dagger, this is the worst case. The ratio test is inconclusive. Meaning I would have to do some kind of comparison test or blah, blah, blah on this. I don't know, don't care. I just wanted to show you a case where the ratio test was inconclusive because the limit ended up equaling 1. All right, so what we've done then is on AP Classroom, we've created some more multiple choice practice. Some of you did that. We put up a 10-point, we put up 2 already, 10.2 and 10.11, because they were things that were on the quiz that you took. I've added now 10.5, 10.7, and 10.8. All of those practice geometric, ratio, alternating, p-series. They're all mixed up for the they're mostly straightforward. And again, if you want geometric again, you can go and practice 10.2 as the practice with geometric. The only one you don't need to, of the AP Classroom quizzes that don't have to do with numeric series, is the 10.11 one, because that's still dealing with power series. All right, so that is our numeric series review. So, as a wrap-up, think about when you want to know if a numeric series converges, the first thing you should always think about is the nth term test for divergence, right? No matter what it looks like. After that, you're like, what should I do? What should I do? Now remember, AP did say that the direct comparison test and the limit comparison tests are not going to be on this year's AP test. So if your nth term test shows that your terms do go to 0, your next shot is to say, does the series look geometric? Does the series look like a p-series? Is the series alternating? Does the series have a bunch of factorials, powers, and exponentials in it? And that helps you decide which one of these 4 tests to run on it. And then remember, geometric test for convergence, you're looking for a common ratio that's less than 1. For a p-series, you're looking for a power that is greater than 1. For the alternating series test, remember you're looking for first an alternating series, second positive terms, and third terms go to 0. And then the ratio test, you have to do the limit of that ratio of consecutive terms, and you want that limit to be less than 1. Your book does have a wrap-up of this, have a page too. I just think it looks a little too mathy, right? I think this, I like this presentation as opposed to that one. But your book on page 521 basically says exactly what I did. The first thing, procedure for determining convergence, the first thing you do is the nth term test. If your terms go to 0, you ask if your terms go to 0. If your answer is no, your series diverges and you're done. If your terms do go to 0, yes, you may converge or you might not. Don't know. So what are the next thing you do? Think geometric. Is it geometric? Convergence, absolute value needs to be of my common ratio needs to be less than 1. If it is not geometric, is it a p-series? Do I have something that looks like 1 over n to the p? Yes, I do. The series converges if that power is greater than 1. If it is not a p-series, you don't have to worry about most of these. Firstly, are all your terms positive? The integral test is not tested this year. The nth root test is not tested this year. Just the ratio test. Right? If your terms are positive, which doesn't actually matter if your terms are positive because you're going to be taking the absolute value anyway, then you go to the ratio test. And if your ratio test, right, that limit is less than 1, then your original series converges. If you do have alternating series, maybe you have an alternating series test, right? Then you run through those 1, 2, 3 conditions, alternating, positive terms, and terms go to 0. And then after that, this nonsense, well, you have to do something more advanced, look at a computer system, blah, blah, blah. That's not going to happen to you. This is what's going to happen to you. It's either going to pass the nth term test for divergence and you don't have to go any further. If it fails the nth term test for divergence, you might have a convergence and you need to check if it's geometric. Is it a p-series? Is it an alternating series? Or is it got factorials and everything and exponentials or lots of powers for you to do the ratio test on? Okay? That's numeric series. I hope you have a good week. Take care.